А если будет
Yes.
оффлайн, то записываться будет?
I hope so. Well, last semester, like I forgot where were, in October, something like this, in November, I forgot. Yeah, they used to have recordings from the room number 208 or something like this.
В следующий раз очно или заочно будет?
Well, I think maybe next time still online, just like today and before, but then I will reconsider once again.
Спасибо.
Thank you. Okay, so so last time we were proving the theorem about this the defect, that the defect was quadratic. So we defined the pairing of line bundles on our product surface as the defect of their tensor product minus defect of the arguments minus defect of the structure sheaf of our surface. And the claim is that this is bi-additive, well, bilinear, and our defect of a line bundle is just 1/2 of its pairing with itself. Okay, and we started proving it. The proof is just sort of explicit calculation, and in order to do this calculation, we view any line bundle, well, up to our equivalence, up to decomposable line bundles, as the one associated to a smooth divisor on a surface, on our surface. So the first part we already did last time was that any line bundle is equivalent modulo the decomposable ones to the one associated to the divisor. So the eyes are smooth disjoint curves.
Эквивалентность в смысле чего? Изоморфная?
No, well, our standard notation, so it means that L is really isomorphic to O of this smooth divisor. Tensor pullback of some line bundle from the curve C, whatever, M1. Tensor the pullback of some other line bundle from the curve S, the M2. Yeah, this our standard notion of equivalence. Yeah. Okay, and we proved this as a corollary of Bertini's theorem. So, well, first note is that there is a very ample line bundle on our surface of the form, well, let me just say, there is a very ample decomposable line bundle on our surface. So it's of the form O, C, so some big number like M times C, tensor OS, some big number multiple of a point like this, and moreover, say L inverse tensor this is also very ample and defines.
Почему он очень обильный, вот этот пучок?
Well, any if you have an ample line bundle, then for any other line bundle, if you twist it with a sufficiently high power of this ample line bundle, then it becomes very ample. We discussed this some time ago. Okay, so that's what happens here, and defines a projective embedding. Yeah, let's denote this line bundle. Well, I'm short of names. Maybe now n, something like this. So our surface C times S into the projectivization of global sections with coefficients in this line bundle dual. Okay, and the linear system of of all the dividers, of all the effective dividers, well, associated to n, that is just zeros of regular sections of n, is nothing but the hyperplane sections of our surface embedded into this projective space. Okay, but then by Bertini theorem,
Но, извините, можно спросить?
yes.
Ну, теорема Бертини, она утверждает, что если взять какое-то открытое плотное подмножество в пространстве гиперплоскостей и пересечь его с какой-то гиперплоскостью...
Not literally so. So we consider hyperplane sections of a smooth variety. In this case, the smooth variety is C times S, our decomposable surface. And then those hyperplane sections are given by all the possible hyperplanes. all the possible hyperplanes, they are just points of the dual projective space. And now it is claimed that for an open, dense subset of this dual projective space, the corresponding hyperplane sections will be all smooth. Okay, so in other words, a general hyperplane section is smooth. That's the content of Bertini theorem, and that's what we are using. And that's what I'm writing down. A general hyperplane section is smooth, and that's it. So it's a union of connected components, and each connected component is smooth, and all the connected components are disjoint by the very definition.
Не совсем понятно. Ну, вот есть у нас вот это проективное вложение.
Yes.
Мы доказали, что произвольная гиперплоскость
not arbitrary, but general, almost any. Yes.
Образует гладкое подмногообразие. Как из этого следует все-таки утверждение, что
almost all hyperplane sections are smooth? That's exactly what we need.
Вот мы хотим доказать изоморфность L вот с таким сдвинутым структурным пучком на такой вот дивизор. Как отсюда это следует?
Divisor. Russian they say divisor. Second,
извините.
We are talking of n. You see, this n is equivalent to L inverse, right? And all the almost all regular sections of n have smooth divisors, smooth zero divisors. That's what we need.
Спасибо.
Okay. Welcome.
I don't still understand. So, okay, you have. So what do you use? You use it. General sections have smooth zero sections.
Divisors, smooth zero divisors.
But then, but then how it is connected with this?
Yes.
Okay, so but now we must prove that it's that our shape is of the form O of sum of di.
No, not quite our shape, but it's equivalent to model decomposable.
Yeah, but our shape, I mean n. What is denoted n should be
right.
Should be equal to.
Well, let me write it down that for any section like this, n is isomorphic to O of D, where D is the zero divisor of this section. Is that what you ask, or?
So this is something. Okay.
And if we take a general global section sigma, then by Bertini theorem, its zero divisor will be smooth.
So what you've written just now is some fact that we use here.
Yes, but we used it many times. Yeah.
Okay.
And now we are using it here. Absolutely right.
Great. Thank you.
Welcome. Okay. So the first part is proved. Now the second part is this explicit calculation that I promised. So the pairing of two line bundles in terms of part A is sum over those smooth connected components, the divisors. Degrees of this divide of the second line bundle restricted to the smooth divisor component plus degree along the first curve of L times degree of along the second curve of N plus vice versa. Like this. Okay, so this is an explicit calculation that will allow, well, for example, from this you already see the bilinearity. Well, more precisely, you see linearity in N, but since it's the definition is symmetric, then it's also linear in L, so it's bilinear. Okay, so let's perform this explicit calculation.
And I forgot why it is symmetric.
Just by the very definition. I mean, let's go back. Here's the definition of the pairing.
Okay.
It's very symmetric.
Okay.
Okay. So we have the following exact sequence. Tensor product goes to N goes to the sum over I and restricted to di. So here we use that L is isomorphic to the structure sheaf.
А как устроены морфизмы в этой точной последовательности?
Well, I just twist by n, so I have 0 to L to O to well, O direct sum of O di's. Okay, just because this L is some ideal sheaf, yeah, subsheaf of the structure sheaf.
Извините, а почему есть точность в среднем члене?
Oh, sorry, I forgot to finish. Well, once again, the upper sequence is the lower one, tensored by n. Yes, so n is invertible sheaf, locally free, so you can tensor with it and it preserves exactness. Do you ask anything about the lower sequence?
Да, вот почему есть точность в среднем члене, нижней последовательности?
Well, I don't even know what to say. Maybe if you think about it a moment, you will have no question.
Хорошо.
Okay. So from this we have the equality of Euler characteristics. So negative chi of L tensor n plus chi of n equals the sum of chi of n restricted to our divisors. And also before twisting by n, negative chi of L plus chi of the structure sheaf equals the sum of Euler characteristics of those divisors. Okay, now let's subtract. And get that negative chi of L tensor n plus chi of n plus chi of L minus chi of the structure sheaf equals sum of the Euler characteristics of the structure sheaves of our divisors plus chi of n restricted to the divisors. And this is nothing but the degrees of n restricted to our divisors, right? Because well, the characteristic of a line bundle on a, so the i's are curves, right? And for each particular curve di, we subtract the Euler characteristic of the structure sheaf from the Euler characteristic of a line bundle, and this difference is just the degree of this line bundle. This is well known and clear, and also let's compute the Euler. So you see, if we go back to the definition, we need to compute something for the tensor product minus something for the factors and something for the structure sheaf. This is our pairing, and now this something is the defect, and the defect of any line bundle. If you remember, well, maybe let me write it down. Here. That the defect of anything like L, for example, is the Euler characteristic along C times Euler characteristic along S minus the Euler characteristic of well, the total Euler characteristic of L. Okay. So we well, when I wrote just chi, I meant chi on this surface, C times S. Okay, so what we computed was some part of what we needed, right? But we also have some other part. Namely, we need the parts along curves, right? We computed the desired summand for the surface, and now we also need to compute the summands for curves along first curve C and along the second curve S. So if we consider along something like this times Euler characteristic along S for L tensor n minus Euler characteristic of L along C times Euler characteristic of L along S minus Euler characteristic of n along C times Euler characteristic of n along S minus the Euler characteristic of the structure sheaf. Yeah, if you again look at this very first formula definition, you also need to subtract the characteristic of the structure sheaf. So.
А чему вот это все большое выражение равно слева, например? Мы же сейчас хотим найти, чему равно спаривание, доказать вот эту теорему.
Yes. So once again, let's well, unfortunately, I need two pages. So first of all, look at the definition of pairing. Yeah, and remember it for a few seconds. Okay. This is in terms of the defect. Now look at the definition of defect itself here. Okay. So we can compute something for the Euler characteristic along the surface And now we need to compute something for all characteristic along the factor curves. Okay, and that's what we do now.
Спасибо.
And when we do this, we just need to know the degrees of these line bundles along our curves. Okay, because all characteristic by Riemann-Roch is expressible via the degree. Okay, and the result is by Riemann-Roch. The result will be the degree along C of L times degree along S of N plus the degree of N along C times degree of L along S. Okay, and that's it. So we performed this check of part B.
Извините, а вот у Кэмпфа
Yes.
еще какое-то странное слагаемое есть, минус сумма пи степени n проекции на эритое.
Yeah, unfortunately, in this part and in so these are last 5 pages of Kempf or something like this, and in these last 5 pages of Kempf there are tens of typos, so it's very sloppy. There are very many typos, and maybe you'd rather use my notes than Kempf. Here he has
Спасибо, понял.
in every line. Okay, so we proved the bilinearity. Okay, and the last thing that remains to prove is that the defect of L is 1/2 of its self-pairing. Okay, and let's compute 1/2 of the self-pairing by linearity. This is minus 1/2 of pairing L and L inverse. Yeah, but by linearity once again, and this is but by definition 1/2 of negative defect of L tensor L inverse, that is just trivial bundle, plus n of L plus plus n of L inverse plus n of the structure sheaf. Okay, and then you have plus n of structure sheaf minus n of structure sheaf. So what remains is just 1/2 of n of L plus n of L inverse. Okay, and so now we need to check the symmetry. That n of L is equal to n of L inverse. And this is essentially the self-duality. For the surface C times S, but we did not prove self-duality in general, even for surfaces, or only for curves. So we'll reduce it.
В какой форме эта дуальность предполагается? Мы писали вроде, что хом есть первый гомологии, двойственная. Или это в какой-то другой форме?
I also formulated the duality in general, that if you have n-dimensional, like here, surface is 2-dimensional, So hi of our surface with coefficients in any, say, vector locally free sheaf F is dual to the 2 minus ith cohomology with coefficients in F dual tensor, the canonical line bundle like this. So it's a perfect pairing.
Из этого будет следовать пункт C.
Right, but we did not prove this, so we'll reduce it to the known third duality for curves.
А как отсюда, если предположить, что мы знаем, что это справедливо, как отсюда пункт C следует, или это какая-то нетривиальная работа?
Well, no, nothing. Just you need Euler characteristic, right? So it implies that the yeah. So the Euler characteristic of these two guys are equal. Of well, chi of F equals chi of F, dual tensor canonical class, but the canonical class is decomposable. It's the product of canonical class lifted from C and from S, and so it's equivalent to F dual. So you will deduce what you need, but well, in fact, we need to check that the defect of L inverse is equal to the defect of L tensor of the canonical class, right? Because this is decomposable.
Если мы умножаем какой-то обратимый пучок на разложимые, то не изменяется дефект, да?
Right. Yeah, that's what we proved last time, a week ago, last Thursday. Welcome. So you see it fall. Well, it's just written in the previous line, so that's what we need, but we don't quite know it. So let's do this in a pedestrian way. So we may use what we proved in the very beginning, namely that our line bundle L is O of some pi. Well, in fact, before we used that L was O of negative sum, but for the same price we can use that L as this O of positive sum, and then we have the exact sequences L inverse to O to the direct sum of O di. We already used it once, and also have that sequence the canonical class of C times S goes to the canonical class of C times S of the sum of di's goes to direct sum over I of canonical line bundles of di's, and this is called the adjunction formula, and we proved it a long time ago. Okay, and from this we deduce that the Euler characteristic of the structure sheaf minus the Euler characteristic of L inverse is equal to the sum of all characteristics of structure sheaves of our divisors, and also all characteristic of the canonical line bundle twisted by our divisor. Oops, sorry, minus, sorry. Minus equals okay. This
Что-то картинка зависла у меня. Что-то вы сейчас писали что-то?
Equal to negative. Yes. Yes.
Что-то у меня все пропало. Ну, то есть я не вижу доски, на которой вы пишете. Не слышу вас.
Hello. Hello.
Сейчас слышу.
Now I can hear you.
Yeah, I'm sorry about this. I have to share my screen again, right?
Yeah.
Let me try. Where are we? Here.
А что было на предыдущей странице?
It shows the previous page for a moment.
Yeah, I'm sorry. Yeah. Sorry. So we take this second sequence. We write the Euler characteristics, and we get this equality at the bottom line, and using the Serre duality for the smooth curves di, we rewrite it as the negative sum of Euler characteristics of the structure sheaves. Okay, and this is what we need. So from this we get that the Euler characteristic of the structure sheaf minus Euler characteristic of L inverse is the Euler characteristic of the structure sheaf. Oh, so sorry, of the canonical class minus the Euler characteristic of canonical class twisted by sum of di's like this, and from this we get that the negative defect of the structure sheaf plus the defect of L inverse is negative defect of the canonical class plus the defect of the canonical class twisted by our divisor. Okay, and well, this is because if we take the Euler characteristic along first curve of the structure sheaf times the same along the second curve minus Euler characteristic of L inverse along C times Euler characteristic of L inverse along S, then it is the Euler characteristic along C of the canonical class times Euler characteristic along S of canonical class minus the Euler characteristic along C of canonical class twisted by divisor times the same along S. Okay, and this is just by shear duality on C and S. Okay, so from this we proved that the defect of L inverse equals the defect of L times the canonical class, and then we know that this is the defect of L because they're equivalent. Okay, so that's all we needed. We proved the theorem, and from this theorem, remember, so we know by now that n of L is first of all well defined on the reduced Picard group. There's the Picard group of our surface modular the decomposable ones. Okay, that n of L is always positive whenever L is non-trivial. And we know that n of L is quadratic. So these are the key points, and from these three key points, it follows just by using Cauchy-Bunyakovsky inequality that the absolute value of the pairing of two line bundles is at most twice square root of n of L, n of n. Okay, and in fact, we only have the equality when they are proportional. Fine, and now, well, already this may be called Castelnuovo-Severi inequality. But now we'll specialize it to some particular line bundles, and then it will be even more classical form of the Castelnuovo-Severi inequality. So well, it will be an application to fixed points of well, for example, of endomorphisms of curves and then next time, or maybe next week, we will consider application to the Frobenius endomorphism of curves over finite fields. But it is more general. It works over arbitrary fields, say in zero quadratic, and with arbitrary endomorphisms, and even more general than this. So let me first formulate something more general. So suppose we have two curves, again C and S, and two morphisms, say F and H, from C to S, two different dominant morphisms. So the most famous example will be when C equals S and F is just the identity, and or maybe H, sorry, H is identity, and F is arbitrary. And then the fixed points of F CF to also say are just intersections of the graph of F with the diagonal, right, inside C times C. Well, and this is C times F. And we are going to write some estimates, some inequality for the cardinality of this. So Castelnuovo, Severi. Estimate for the cardinality of the fixed point set. Okay, so, but this was the most famous example, and we are back to our most general formulation. In our most general formulation, the curves are not necessarily isomorphic. There are two different curves, C and S, and we have two morphisms. So in this famous application, one of them was identity. In general case, they are on equal footing, but just two arbitrary morphisms. And now to make contact with the previous study, we take L is a structure sheaf twisted by divisor negative graph of F, and N is symmetrically structure sheaf twisted by negative graph of H. Okay, and now we define the pairing of F and H of two morphisms from one curve to another curve as the negative degree of N restricted to a graph of f. Okay, and in fact, this is the same as the the number of points in the intersection of gamma f and gamma h, but we need to, you see, the two graphs may have tangent point. Yes, so this is literally so if the intersections are transverse, but in general this is only morally so, and more rigorously, it is really the dimension over our base field of the global sections of some skyscraper sheaf, namely the structure sheaf modulo the ideal sheaf of the first graph plus the ideal sheaf of the second graph.
Как это увидеть? Вот последнее равенство.
The question is about the degree of the second bundle restricted to the first graph. Yeah, that's the question. Yeah, that's what you ask, I hope. Right?
Я хочу вот понять, как вот почему минус степень n ограниченная на граф f равна размерности сечения вот такого c на s.
So, well, this is also equal to the degree of O p times s of gamma h restricted to gamma f. Okay, like this, and well, this is more or less the definition. Yeah, the ideal of well, I don't know. Maybe let me try to fit it here, since the ideal of gamma f is O of negative gamma f. Yeah, our graph is a divisor, right? It's the product of curves is a surface. The graph is a curve, so it's a divisor, a smooth divisor in this surface. Yeah, and the ideal sheaf of this divisor is just by the very definition, it's O of this negative divisor. Okay, so that's what we have by definition.
Is it true that we in fact can define the intersection of these graphs, but it is not a variety, but it's rather
absolutely right. We will talk about schemes next week, and the intersection of the graphs at tangent points, it acquires nilpotence. So it's a zero-dimensional scheme, but not necessarily a variety.
Okay, thank you.
But in general, if the two morphisms are in general position and their graphs intersect transversely, then there is no need in these quotation marks. It will be literally just the cardinality of their intersection. And in general, it's only an upper estimate. Okay, so the next theorem we are going to prove is well, again, so to say, Castelnova. Severi inequality. And it says that the absolute value of degree of f plus degree of h minus their pairing is at most twice the square root of genus of the curve S plus genus of the curve C times degree of f minus 1 times the genus of C, sorry, genus of S, sorry, plus genus of C times degree of H minus 1. Like this, but maybe we need absolute values rather, because no, we don't need absolute values because both things are non-negative. Yeah, the degree cannot be negative, and the genus also cannot be negative, so it's fine. Okay, so let's prove this, and then maybe next week or even next time we will apply this to counting points on curves over finite fields, and this will result in the so-called Riemann hypothesis. It's somehow the most famous of André conjectures about points on curves over finite fields. But strictly speaking, the derivation of this Riemann hypothesis is given in the next home assignment. And next time or next week, I will just explain what does it have to do with counting points over finite fields. But you will have to apply this Castellanova-Severi inequality yourself in the next home assignment. Okay, so let's prove this. And what do we need to check? You see, we already had this Castellanova-Severi inequality in abstract setting. We only have to match the notions for line bundles to the notions for morphisms. Okay, namely, I claim that the left-hand side in this corollary is literally the left-hand side in the theorem, and the same for right-hand side. So we need to check first that the pairing of L and N bundles is the degree of F plus degree of H minus pairing of F and H. And second, that the defect of L is the first factor, so GS, the genus of S plus genus of C times degree of F minus 1, and the defect of N is again genus of S plus genus of C times degree of h minus 1. But these are symmetric, so we only need to check the first one. Okay, so so let's do this. And for the first part, it's almost immediate. So we know that the degree of f equals the degree along C of L times the degree of along S of N. Why this is so? Let's just recall what is L. So L was defined here. It's O of negative graph of F, and L is O of negative graph of H. So the degree of L along C is what? Let's discuss this. Say, Shuai, can you tell me what is the degree of L along C? Yeah, Shuai?
Yes, sir.
Yes.
But I'm really sorry. I actually lost a lot.
Okay, then maybe Leonid, can you tell me what is the degree of L along C? So you see,
No, I think no.
And it is the graph of some function, so to say, like this. So what is degree along C? Yeah. Did you tell me? I didn't hear, Leonid.
No, I don't. I don't know.
And Altan, do you know?
I can only guess.
Yes.
Okay. What could it be? Could be 1. Or
So but by definition, we have to take any fiber like this, for example. Yeah, restrict to it and find the degree. And when we take the degree along S, we need to take any vertical fiber like this, and restrict there. So what do we get? So when we restrict to the vertical fiber, we get degree -1, right? Because the graph intersects this vertical fiber at just one point, right?
Михаил Владимирович, можете, пожалуйста, напомнить, выписать определение степени от О от минус графа? Это будет в течение вот таких вот, ну, можете напомнить, выписать.
Yeah, the degree along C of any line bundle is the degree of this line bundle restricted to C times S for any fiber. Okay. So you just restrict to any fiber and consider degree. And well, just intersect this fiber with the graph, and the yellow fiber intersects this graph in just one point, and the red fiber intersects this graph in degree of f points. Okay.
Спасибо.
So that's what we get here, and then symmetrically degree of H will be equal to degree along C of n times the degree along S of L. Okay, and finally the negative pairing of F and H is equal to the degree of n restricted to the graph of F. Just by definition, if you see the definition, it's just this. Okay, fine. So we are done with part 1, and now I have to check part 2, namely the first. The second is symmetric. So we have to check that n of L is equal to genus of.
Владимирович, можно спросить вас?
Yes.
А почему в определении вот этого спаривания f с h возникает знак минус, и при этом у нас это ассоциируется с количеством точек пересечения графов? То есть это больше нуля получается.
Right, because our line bundles were negative, you see, by definition. L is O of negative graph. So graph is an effective divisor.
Да, все, спасибо.
Okay, so we're trying to compute this. Genus of S plus genus of C times degree of F minus 1. Okay, so we need to recall that L is the structure sheaf twisted by negative divisor gamma F, the graph of F. And let's consider an exact sequence. This ideal sheaf goes to the structure sheaf, goes to the structure sheaf of the graph. Okay, and hence we can compute the Euler characteristic of the line bundle here equals the Euler characteristic of the structure sheaf minus Euler characteristic of the graph, and the graph is isomorphic to the curve C, right? And so it is just Euler characteristic of the curve C.
Почему граф изоморфен кривой C?
By projection to C. We just saw this in this picture. The graph projects to C isomorphically, but to S with degree of F, right?
Да, спасибо.
Okay. So let's compute the defect of this line bundle equals the Euler characteristic of I don't need to write C here. Of this minus 1 times the Euler characteristic of OS minus degree of F minus the Euler characteristic of the structure sheaf plus the Euler characteristic of OC, and this is well, you see, we have this product, and in this product we have the Euler characteristic of OC times Euler characteristic of OS, and three more summands, right? And then we subtract the Euler characteristic of the surface, C times S. So it kills the product, right? I mean, the Euler characteristic of OC times Euler characteristic of OS is equal to Euler characteristic of OC times S.
Вот, Леныч, извините,
Yes.
немножко запутался. Вот этот дефект от структурного пучка C на S минус граф F равно
Yes.
после вот этого равенства. Чем мы воспользовались? Почему такая формула возникла?
Just by definition, because the defect is the product of Euler characteristics. Sorry. The defect of anything M is the Euler characteristic along C times Euler characteristic along S minus the Euler characteristic on the whole surface. Okay.
И почему дефект вдоль оси вот этого структурного пучка сдвинутого графа получается Эйлеровая характеристика структурного пучка на оси минус 1?
Because well, well, look here. We restrict to the yellow fiber, right? Then on this yellow fiber, our sheaf. Well, where should I write it? O ES of minus gamma F restricted to C times S is just oh, sorry, not C times S. It's sorry. The yellow fiber is small c times big S, right? And this is just O of S minus F of small c. Do you agree? Yeah.
Да.
So you take the vertical curve S and you twist it by some divisor of degree 1, well, minus 1. Okay, so the Euler characteristic here is equal to the Euler characteristic of OS minus 1. Yeah.
Спасибо.
Just because the degree dropped just by 1, and if we restricted it to the horizontal red fiber, then the degree would drop by the degree of F. Yeah, but for the same reason, and that's what we use here.
Спасибо большое.
So in this product of two brackets, that's what we just saw. Okay, so this was all some extra recollections, and well, maybe let me just encircle what we need here. Yeah, there are, well, three summands. One product minus Euler characteristic of the structure sheaf plus Euler characteristic of the curve. Okay, so we're continuing with this computation. This is, and I said that the product part cancels out. Yes, because it's Euler heuristic of OC times Euler heuristic of OS minus Euler heuristic of OC times S. This part cancels out. What remains is negative Euler heuristic of OS minus Euler heuristic of OC times degree of F minus 1 plus degree of F. And now here again, you know that the Euler heuristic of OS is 1 minus the genus of S, right? So here we get genus of S minus 1 plus genus of C minus 1 times degree of F minus 1 plus degree of F. Okay, and now degree of F cancels out, and you get just genus of S plus genus of C times degree of F minus 1, and that's what we wanted, right? In the very first line, that's exactly what we wanted. So there we are, and we proved the Castelnuovo-Severi inequality. Okay. Now, now maybe I'd rather stop here, because next time we'll prove subversion of Riemann-Roch theorem for surfaces, not necessarily decomposable surfaces, like not necessarily product of curves, just arbitrary surface and arbitrary line bundle on the surface. We will compute the Euler characteristic of this surface with the coefficients of this line bundle. Okay, and then we'll discuss notion of schemes, the general notion of schemes, and then we'll apply it to some curves over finite fields. Okay, these are some basic examples of schemes, and we will be able to apply Castelnuovo-Severi inequality to graphs of Frobenius and count the number of points over finite fields. Okay, so.
And is there a lot to say about schemes, or will be? No.
I will say almost nothing. I will just formulate the general definition, and then I will proclaim that everything we proved for varieties generalizes straightforwardly to schemes.
And why to bother with variety? Why bother with varieties and not to work with schemes all along?
At the very beginning, yeah, that's a question of psychology. Maybe I should have done as you say, but well, you see, with varieties, there was some intuitive point that they were ringed by functions. Yeah, but it does not work as this with schemes. Schemes are ringed by something abstract, and with varieties you can always think of them as usual varieties, but with schemes you cannot quite. But still, after you have such a big intuition as we developed already, then it's already fine to just proclaim that everything works the same way for schemes. But if you start with schemes, at least for me, it would be somewhat counterintuitive. So there will be some extra differences, extra difficulties that aren't actually there. You just have to get used to this language of sheaves and structure sheaves, and then you see that the structure sheaf that does not have to consist of functions. Just structure sheaf, and that's it. Okay, that was an apology for schemes. So, any other questions, suggestions?
Михаил Владимирович, а вот единственное место, в котором мы использовали, что у нас группа Пикара проведенная, это то место, где мы показывали, что пучок L эквивалентен структурному пучку, крестованному на вот эти кривые, которые...
Yes, we use this.
И больше нигде это не требовалось.
Well, somehow this defect and the pairing are defined on the reduced Picard group. Yeah. But we used it in calculation at this point, but otherwise we could not formulate this positive definiteness, right? The positive definiteness does not work for the whole Picard group because it is just 0 for decomposable line bundle.
Спасибо.
Welcome.
А есть какой-нибудь несложный пример, где вот это все можно вручную посчитать? То есть все эти n от L.
But well, in a sense, that's what we were doing, right? For this example with the graph, that's what we did. We computed everything explicitly. So to say, in elementary geometric term. Didn't we?
Ну, да. А есть как бы еще проще? Ну, то есть еще более конкретный.
Well, maybe when the curves, that's what I mentioned, when the two curves are the same, one morphism is identity, that is, the graph is diagonal, and we're just counting the number of fixed points of the other, and the morphism.
Ну, да, хорошо.
Well, I don't know anything even more explicit.
Maybe take a projective line and some meromorphic function on it. And,
yeah, okay. Okay, and by the way, Altan, if you come back to Moscow, will you be willing to come in person to lectures?
I think yes.
Okay.
But I think there is some demand for online lectures. I don't know.
They will be recorded, certainly. Yes.
Okay.
And maybe even there will be a live broadcast. Okay, so then we will reconsider next week and maybe start offline. We'll switch to offline mode next week, maybe. Okay, so thank you. I'm stopping the recording and saving the notes and saying goodbye to everybody.